Question 11. So we have a circuit, and in this circuit, we have a ammeter connected next to the battery, and we have a lamp, and we have another lamp connected in parallel, because we can see that clearly the current splits at this junction and then joins up back at this junction to go back to the battery. So therefore we know that this is a parallel circuit. So in which position could a switch be placed so that both lamps can be switched on or off at the same time? And that will be position M, because that is going straight back to the battery. And if this part is broken, the current has no path to go around this route or around this route here, because they both pass M. So draw a circuit a symbol for a switch, and there we go, we've got an open switch, and that's a circuit symbol for that. And what we are trying to find in this part C is the current in the battery, providing that we've got the time um, and the amount of charge that is flowing through the battery. So in 30 seconds, 24 coulombs of charge flow through the battery. So what's the current? Current is charge divided by time, 24 over 30, 0.8 amps. We've got a potential difference of 3.6 volts, and we want to try to find the energy transferred when 60 coulombs is of charge is flowing through the battery. So we've got charge and we've got voltage, and we want to work out energy, and the formula that connect all three is energy equals charge times potential difference, and potential difference of voltage are the same thing. So energy equals charge times potential difference, which is 60 as the charge, and potential difference is 3.6. So 60 multiplied by 3.6, which is 216 joules of energy is transferred when 60 coulombs of charge flows through a battery with a potential difference of 3.6 volts. So what we've got here is two circuits. Circuit X, we can see that's a parallel circuit, and circuit Y, we can see that is a series circuit. We got an ammeter there connected close to the battery, an ammeter close to the battery there as well. And how would the reading on the ammeter in circuit Y compare to the reading on the ammeter in circuit X? Now, we've got two lamps here, and we've got the same two lamps here. In series, the resistance of this and the resistance of this add up and give you a high resistance, and that means that the current here will be relatively low. When we add more and more components in a parallel circuit, now these two will carry on working the way they are. The additional component will get more current, and as a result, more current will be drawn from the battery. So complete opposite. So the reading on Y will be lower, so the current reading here will be less than the current reading there. So how does the total resistance of the circuit in Y compare with the total resistance in X? And as we saw, when we connect the same components in parallel, the total resistance drops. So this will be low. And when we connect two components in series, the total resistance gets high and the current will drop. And as a result, the resistance is high. So the total resistance is high here, total resistance is low because there's more current going through that. And the student built another circuit. So here we have one light bulb inside that particular circuit. What we are asked to do is calculate the resistance of the lamp. And we know that 3.6 volts is around the lamp. And we know that if 3.6 volts is from the battery, it all goes through the lamp. So we know that's 3.6 volts here. We know that the current through the lamp is 0.8. So we want to find a formula that links the current and the voltage and the resistance. And that's resistance equals voltage over current. So 3.6 divided by 0.8, which is 4.5 ohms.